Okay, one of the things that we're going to be asked to do here is to simplify expressions, okay, using some of our identities that we have possibly. So in this particular case, it says simplify the cosine cubed of x plus cosine x sine squared x. Okay. And so I want you to take a look at the steps on this side. Okay. And I also want to relate this to the opener that we did today. If you remember, two of the things that we did in the opener are going to be very important to what we're going to be dealing with simplifying these identities, okay, or simplifying expressions. And one of them is factoring. Okay. That's going to be one strategy that you always want to try to look for. Is there anything that can be factored? Okay. So looking at these two expressions, cosine cubed and then cosine x sine squared x, okay, you'll notice that they both have a cosine x in common. True? So it's kind of like what we learned in algebra, that the first thing you want to look for is, do they have a GCF? Do they have any kind of greatest common factor? Okay, in this case, they both have a cosine squared x. So then what we want to do then is factor that out. So we'll take that cosine x out, and we'll be left with cosine squared x plus sine squared x. Fair enough? Okay. All right, so once you do that factoring, and then what we do next is look for anything that we know in terms of identities that we just discussed. Okay, what do we know about cosine squared x plus sine squared x? It's 1. So really, isn't that expression simplified to simply cosine x? Absolutely. Okay. And if you don't believe it, okay, take your calculator and put an x into that expression, and then put the same x into this expression, and if it is true, then you should get what? Should get the same answer. Fair enough? Okay, so you can test that when you get done to make sure that it is, in fact, an identity when you get finished by testing it with some value. Now, if you pick one value and see that it's right, does that guarantee that you're right? No. I mean, ultimately, if you wanted to prove that it was true by examples, you'd have to show all the examples, which means you'd have to put every angle possible in there, which is impossible, right? So ultimately, the algebra part of this is what gets us from one to the other. Factoring is a valid step. Using the Pythagorean identity is a valid step. So if we do both of those correctly, okay, we should get an identity when we're done. Okay. All right. Let's take a look at another one here. It says to simplify this expression. All right. Another thing that you want to look for besides factoring is there any expanding I could do here? Okay. Because obviously the top bar is already factored. Okay. What if I were to expand this? Maybe something will appear if I do some expansion. So let's go ahead and expand that. We'll go ahead and multiply cosecant times cosecant and so on. Use the FOIL method, of course. You'll see how this works out. All right. If we were to FOIL that, recognizing that these two are conjugates, they have the same binomial, but we have two different signs. Okay, so that means we really don't have to bother doing the inside and the outside on the FOIL. We could just do the first and the last. So we'd end up with cosecant squared minus 1 over cosine squared. Okay, and this part right here just tells us why we got this, because we FOILed it essentially and got first, in this case, minus last. Okay, and then from there, let's think about what we know about this. Okay, we have cosecant squared minus 1. Okay, now we just had an identity a couple minutes ago that had cosecant squared in it, didn't we? Okay, so that might be something that we could do. We could replace cosecant squared with what it equals. Okay, and in fact, that's exactly what they just did here. Cotangent squared x, okay, is equal to cosecant squared minus 1 because we said in our identity that cotangent squared x plus 1 was equal to cosecant squared. Okay, and recognize that if I were to subtract 1 from this, I would solve this for cotangent squared. So wouldn't cosecant minus 1 equal cotangent? Okay, because this sentence is true. Okay. Now I got it to this point right now. Okay, is there more I can do? Okay, is there more I can do? Okay. What you want to do next, and this is another general strategy besides factoring, expanding, putting fractions together. Okay, those are 3 so far that we've discussed. Okay, another good general strategy, especially with trigonometric functions, because it wouldn't really work with any other functions, is that if we have anything that is not in terms of sine and cosine, okay, go ahead and put it in terms of sine and cosine. Okay, so the other identity that we're going to use here is we're going to get rid of this tangent by writing it as cosine squared over sine squared. Okay, So if we do that, okay, of course we'd have that. Here's your cotangent squared right here. And then instead of dividing by cosine squared, okay, we'll multiply by the reciprocal of cosine squared, and look what happens nicely. Okay. In this case, the cosine squareds would cancel out, wouldn't they? Okay. All right. So again, ultimately, we're replacing cotangent theta with cosine over sine. Okay. Which, if cotangent is squared, we replace it with cosine squared over sine squared. Okay. Now again, those two will cancel out, and that'll leave us with 1 over sine squared. And to make that even more compact, we can replace it with its equivalent, which what's the same as 1 over sine? It's cosecant, so the final answer here then would be cosecant squared x. Fair enough? Okay.
Do we have to do that? Like, you know, if we're given multiple choice in the test, what will be there, 1 over sine squared x or cosecant squared?
Well, ultimately on the test, you're going to have to be able to produce these steps for me. So when you're on the Math Excel, though, you're not going to be able to write down the steps for the computer to see. Okay, but you're going to want to do this every time so that, you know, when you comes test time, you're actually able to produce this work. Yeah. Yes. So if it's on Math Excel and it's multiple choice, you're ultimately going to need to do this to get to whatever the right one is. It's probably not going to be terribly obvious. You know, ultimately, if it's multiple choice, could you put a number in here and a number in here and see which one is equal to each other? Yeah, you could do that. You can get around actually doing this work, but come test time, it's not going to help you much, right? So you're going to want to go through these steps each time.
When you're checking your answers, do you want to be in radians or degrees? Does it not matter?
Really doesn't matter. So anyway, pretty rare if we use degrees from here on out in any capacity. So, you know, you'd only put it back in degrees as if there's a problem that gave you degrees, I would say, or it said, you know, give it in degrees. All right, good questions. Okay, next I want to look at, this one says find all the values between 0 and 2 pi that solve this equation. Okay, part of our work is going to be doing some equation solving as well. Okay. All right, so I want you to see the steps here of solving this equation. We have sine cubed x over tangent x. Sorry, excuse me, sine cubed over cosine equals tangent. Okay, the first step here is to change the tangent into sine over cosine. Okay, that's good. Keep in mind that there's almost always more than one way to solve a problem here, but they chose to go ahead and change it to sine over cosine. Okay. All right. And then over here, okay, the question is, what did we do here? Okay, how did we get to sine cubed x equals sine x? Ultimately, if we use the cross product property here, okay, we get sine cubed x cosine x equals sine x over cosine x. True? All right. And then we'd have cosine on both sides. Okay, they divided by the cosine and got down to sine cubed x equals sine x. Okay, and again, that's okay. There's one problem with that method, though, that I'm going to talk about in just a minute. But once we get to that point, then what we're going to do is, and this is going to happen a lot in equations, we're going to get everything on the same side and set it equal to 0. We're going to kind of treat it like it's a polynomial. Okay, we've had a lot of experience solving polynomial equations, and if you look at it, wouldn't this be of the form u cubed minus u? Okay, and in that case, what would we do? We'd factor out u, okay, and we'd have sine squared, or excuse me, just sine, that is, equals sine, or times sine squared minus 1. And the other thing that you want to notice here is that this is a difference of two perfect squares. Okay, and hence we would get either two solutions, or we could change that to cosine squared, because that's what cosine squared is equal to. And then bottom line, we're going to use the zero product property. Now I'm going to give you an alternate way to solve this in just a minute. Okay, but like I said a minute ago, I do want to talk about this step up here where they got rid of the cosines. Okay. All right, so with this said, if we have sine x equals 0, okay, what's going to make sine equal 0? Well, we know sine is 0 at 0, pi, 2 pi, negative pi, and so on. And remember, they asked us to find all the solutions between 0 and 2 pi, not including 2 pi. So that means that those two right there should be solutions. Okay. And then also cosine x equaling 0, because if cosine squared equals 0, then we're looking for when does cosine equal 0. That would be at pi over 2, 3 pi over 2. Okay. Both of those are between 0 and 2 pi. So we would keep both of those, but there's a problem. Okay. If we go to check that, okay, what's going to happen if we try to put a pi over 2 into this original sentence? Is that going to work? No. Is 3 pi over 2 going to work? No, those will both give me 0 on the bottom. So even though they seem to be solutions, okay, are they? No. So really the only two solutions to this are 0 and pi. Okay. Now one thing you want to do is recognize at the beginning of this, we could have looked at this and said, all right, well we know that since there's a cosine on the bottom, okay, we know that pi over 2 and 3 pi over 2 are not even in the domain at this point, right? And that's why doing this step by dividing both sides by cosine was okay in this problem, okay, because we're getting rid of the solutions that aren't going to work anyway. Fair enough? Okay. All right. And like I said, I told you I was going to give you an alternate way to look at this, and we'll do that now. If I had sine cubed x over cosine x equals tangent x. Okay. Keep in mind another way to think of that other step would be if I were just to multiply both sides by cosine here, I'd be left with sine cubed x equals tangent x cosine x. All right. And if you look at the right side here, and I change the tangent to what it's equal to, what would happen to those cosines anyway? Yeah, those would cancel out. So that's really the more valid step, the more valid way to get rid of the cosine, if you will, in this case. And notice that, well, what are we back to when we're done? We're back to exactly where we started there. Okay. Now I do want to show you the alternate way to finish the problem also. Okay. I would write it as sine cubed x minus sine x equals 0. And then when I do the factoring out part, I would take all three of these and set them equal to 0, because remember this right here would be sine x minus 1, sine x plus 1. So I'd have sine x minus 1 equals 0, sine x plus 1 equals 0. And then I'd have my 0 and my pi here. I'm not going to use 2 pi because it's out of the domain they gave us. They gave us 0 to 2 pi, not including 2 pi. And then what about this one? If I had sine x equals 1, sine x equals 1 at pi over 2, doesn't it? Okay. Sine x equals negative 1 at 3 pi over 2. But once again, when we do this, key element here is make sure we check these values and that they actually work. Because once we try to take those two and plug them back into the cosine on the bottom, we're going to get a 0 on the bottom situation, and that's going to give us a non-solution, isn't it? Okay. So we got to be careful when we're doing this, because when we do these steps that technically are what we call non-reversible, okay, we sometimes get extraneous solutions. Okay, we get solutions that don't actually work. So when we're solving equations like that, okay, no matter how many answers you seem to have, okay, make sure you check all of them and that all of them work. Okay, because if they don't, then you don't want to use those. That's not going to be part of your solution set. Okay, questions so far?